Hello, welcome back to the class. So again, this comes under module 2. This is limit state of collapse shear. Okay. So let us consider a beam of span L subjected to uniformly distributed load of W. If I draw a bending moment diagram for this, the bending moment diagram will come like this, where we get maximum bending moment at the mid span. So this is the bending moment diagram. So if I take this beam and if I assume this beam as a rectangular section, so what I see in the beam is this. So it will have certain overall depth and and of course the same span. So let me assume this as a homogeneous beam. Homogeneous is, it is not RCC, just consisting of the same material throughout. Okay. So if I take any two sections of dx apart, slightly thin section, so I can draw that like this here, two sections. And if I take this section is going to be subjected to a bending moment of say M. And if I go little bit this side for a distance of dx, the bending moment here will be M plus delta M. Okay. So this may be plus or minus. So in this case, as we move towards the center, so this is going to be plus. If you take the same section on this side, it is going to be M minus of delta M. It doesn't matter. So there is going to be variation in bending moment diagram. So what I do is I am going to draw the stress variation diagram for this. Sorry, that is at this section. So if this is the neutral plane and if I assume the variation of stress is elastic, then the stress variation diagram will be like this. Let C be the stress at the extreme fiber. Again, if I take this section and draw the stress variation diagram, which I am going to write on this side because I have got some space on that side. So what I am going to get is, again the stress variation diagram is going to be linear within elastic limit, and the stress is not going to be C, it is going to be C plus delta C. So I am not worried about this part because the concept is the same. So C here, C plus delta C here. If I take any fiber of the beam at this level, the stress will be some value, say C dash. And if you take at the same level here on this side, it is going to be C dash plus delta C dash. There is going to be variation. So if I take here the stress is say C dash, if I take at this point the stress is going to be C dash, the stress is going to be C dash plus delta C dash. So look here. So there is going to be change in the horizontal stress here. from this section to this section. To maintain equilibrium, what happens is there is going to be a stress of magnitude C dash plus delta C dash minus of C dash, that is going to be delta C dash. So this imbalance of force or stress gives rise to shear stress. Is it clear? So by principle of complementary shear, the same stress will be developed all around. So what it means is I am going to take an element of certain dimension. So I am going to take this square element. Okay, for my convenience, if you want to take, you can take a rectangular element, it does not matter. So here I am going to take a small element, and instead of calling dc dash, so I am going to call that as force, and if I convert that force into stress at this section, it is going to be Q. Okay. So the direction, let me assume this stress as this way. Is it clear to you? Then when you apply or when you subject the element to shear stress, of course when you are dealing with the problems, you need to convert the stress into shear force. Here there is going to be shear force because it is going to be acting over the entire width of the beam. Okay, when you convert that into stress, so it is going to be Q. Okay, to maintain equilibrium, there is going to be equal and opposite force on this side, and if you convert that into stress by dividing that force by the area, then it is going to be the same Q. Okay. So, but this forms a couple, and that couple is going to rotate the element in this direction, in the counterclockwise direction. To counter that, there is going to be equal and opposite couple to maintain equilibrium. And that force, if you convert or if you calculate that stress, again that stress will be Q. This is called the principle of complementary shear. Is it clear to you? So if I take this element, if I apply some force, and if that force, using that force, if you convert that stress, that is going to be Q. So there is going to be Q in the opposite direction to maintain translatory equilibrium, but this will try to rotate the body. Again, to maintain rotational equilibrium, there is going to be equal and opposite force. Okay, that force, if you convert that into stress, it is going to be Q. This is called the principle of complementary shear. Okay. So I am not going to dictate notes for you. So if I take concrete, if I explain this with respect to the concrete, if I take an element, say ABCD for concrete, okay, or any element for that matter, stress Q, then to counter that, stress Q, and this is Q. If I take this diagonal, what happens is, this diagonal is going to be subjected to a tensile force. Okay? If you convert the tensile force into the stress by dividing the tensile force by this length and the thickness of the element, you are going to get the stress of magnitude Q. Similarly, if I take the same element, I am writing the same element. If you want, you can draw on this figure itself, but I am not going to do that. I am going to take the same element. Okay, this is Q, Q, and if I consider this diagonal, so then this diagonal is going to be subjected to compression. And this holds good for any material, but we are only worried about the concrete. Okay. So when you subject this diagonal of the concrete element is going to be subjected to tension, and this diagonal that is shown here is going to be subjected to compression. Because the concrete is weak in tension, what happens? Concrete cracks. So, whenever you subject a concrete element into shear, that is going to fail due to diagonal tension. This is diagonal tension. And if you reinforce this so that it does not fail due to diagonal tension, if at all you load the beam in such a way that it should fail due to shear, then it is going to fail due to diagonal compression. That rarely happens. When you provide too much shear reinforcement, then it may fail due to diagonal compression, but normally that is not going to happen. Okay? And this diagonal tension failure we are going to worry about. Okay? And for this reason we are going to provide shear reinforcement in an RCC beam. Is it clear to you? So let us take again an RCC beam. For now, for time being, I am going to forget this tension reinforcement. Again, the element, same element, and it is going to be subjected to shear stress Q. So for this RCC element, or RCC beam, two sections dx apart, okay, due to diagonal tension, the concrete will be subjected to tension like this. Okay, to avoid, if at all, if you assume this pure concrete beam, if you keep loading this, and if you are forcing that beam to fail, not in bending but in shear, so we can make it fail due to shear by loading bar, by adjusting the loads. Then it is going to fail along this. That's why you see cracks, diagonal cracks here. Those are shear failures. So when you subject a beam into shear stress, that is an RCC or concrete beam into shear stress, it always fails due to diagonal tension. So to take care of that failure, what we do is we are going to provide reinforcement. Those reinforcements are called shear reinforcements. So what are the kinds of shear reinforcements we can provide? So this is Q, this is Q, Q, I said if it fails due to diagonal tension like this. Like this, same element. So to avoid this kind of failure, what we do is we are going to provide bars in this direction. That is reinforcement bars. So when it is subjected to diagonal tensions, these inclined bars are going to take care of those tensile stresses. They bear the tensile stresses, that way the diagonal cracks are avoided. So these bars may be bent up bars. If you are providing reinforcement here at the bottom, some bars are bent up, or if you want, you can avoid that and you can provide vertical stirrups to take care of shear. So those vertical stirrups are provided like this. So these vertical stirrups will carry certain amount of shear force. Say this will have a component in this direction. Okay, that force, that is resisting force in the stirrups will have a component in this direction. Okay, those resisting forces are going to resist the diagonal tension developed in the concrete. Is it clear to you? So to take care of shear, we can provide bent up bars or inclined stirrups or vertical stirrups. Okay. How we are going to provide stirrups? Yes, if I take a beam here and if I provide tension reinforcement in a singly reinforced section, and if I take a section here, I am going to see this rectangular section like this. So we are going to provide some bars in the tension zone to take care of bending. To take care of shear, what we do is we are going to provide stirrups here. To put the stirrups in position, what we need to do is we need to provide some nominal reinforcements here. So these nominal reinforcements are provided to anchor the stirrups. So this is true in terms of when you design a beam as singly reinforced. When you design this beam as doubly reinforced, you don't have to worry about it because you are going to provide some tension reinforcement and also you are going to provide some compression reinforcement to take care of compression. So those reinforcements are going to work as anchor for these stirrups. Okay. So we are going to provide stirrups at certain spacing, whatever the design requires. And this is called two-legged stirrups. Two-leg in the sense, if you take the stirrup separately, you must have seen in many residential buildings, so they are going to bend the bar like this, and this will have two legs. Okay, if you cut like this, you will see two legs. So this is a stirrup of two legs. Okay. So if the beam is wide, in heavy beams we do that. If the beam is wide, if we are providing too many reinforcements, okay, If the beam is wide, normally we go for doubly reinforced beam. If not doubly reinforced, if you are giving singly reinforced section, still we need to provide some nominal reinforcements here to anchor the stirrups. So in this case, what we do is we are going to provide a stirrup like this. We are going to anchor the stirrup to one of the bars in the compression zone. Always keep in mind, so we have to put these anchors in the compression zone, not in the tension zone. So similarly, what we do is we are going to provide another stirrup like this. So totally we have 2 stirrups and each stirrup will have 2 legs. Totally we have 4 legs. So in the case of design, we need to consider 4-legged stirrups. Here in this case, this is 2-legged stirrups. And of course this will be more effective in carrying more. No, I don't say more effective, this will carry more shear because we have 4 legs. And this will have 2 legs. Again, whether we provide 2-leg stirrups, even 6-leg stirrups or 5-leg stirrups, depends on the size of the beam, and also that depends on the design requirements. Is it clear to you? Next, here, what kind of stirrup? Of course, we are going to provide these stirrups. And what are the diameters normally we go for? Normally, whenever we provide stirrups, so we are going to go for 6 millimeter and 8 millimeter. And if the construction is heavy construction to carry heavy loads, and if the beam size is too big, sometimes they may even go for 10 mm diameter size stirrups. Is it clear to you? So stirrups serve as the member or the steel to take care of shear. What is the other way you can take care? So you can, if you are providing too many or more than 2 reinforcements at the bottom, so as we move towards the support, the bending moment decreases. Because when we design to take care of bending moment, so we are going to design where we have the maximum bending moment. At the section of maximum bending moment, we need maximum shear, maximum area of steel to take care of bending. As we move towards this support, what happens to the bending moment? It keeps decreasing. As a result, what we need is we need less reinforcement. So in such cases, what we can do is we can cut some of the reinforcements, or we can bend some of the reinforcements, and those bent up bars serve as shear reinforcements. In any RCC beam, load will be taken by concrete, that is shear load I am talking about now, then stirrups and bent up bars. And also if you are providing inclined stirrups, okay, they also take some shear force. So these are the 4 components of an RCC beam that takes care of shear. Again I repeat, concrete is going to take care of shear, and stirrups, vertical stirrups, then inclined stirrups and inclined bars. So it is not necessary that we have to provide everything at the same time. So if we don't provide bent up bars here, that's fine. So if you provide only the vertical stirrups, then shear will be taken care by automatically by concrete and the vertical stirrups. Okay. So it is better to avoid all those bent up bars. for ordinary, beams for residential buildings. So this is the way we provide shear reinforcements. Then, what are the factors affecting shear resistance of an RC member? What are the factors? So the shear resistance of rectangular beams without shear reinforcement depends on the following factors: grade of concrete, percentage and grade of longitudinal tensile reinforcement, ratio of shear span to effective depth. I am going to tell you what it is: compressive force, compressive reinforcement, axial compression force, and shear reinforcement. So these are the things that affect the shear strength of a section. So as I said, types of shear reinforcement are concrete, then inclined bars, bent up bars, and vertical stirrups. So stirrups may be of two-legged, minimum two-legged you need to provide. It may be four-legged. If you provide one more, if you have one more reinforcement here, you can increase, you can provide one more here. So it may be five-legged, six-legged. So if you go to heavy constructions, you will see even 8-10 legs of stirrups to take care of shear. So it is very important that you provide not only the tension reinforcement and compression reinforcement if required, you must provide the reinforcement to take care of shear as well. Is it clear to you? Now, what are the critical sections for shear? Here, this is the BMD. If I draw shear force diagram, for UDL, I am going to get the shear force diagram like this. This is WL by 2, this is WL by 2. So we have got, for bending moment, we have got maximum bending moment at the midsection. For shear force, we have got maximum shear force at the supports. So that's why what we need is, we need stirrups at closer spacing near the support to certain length. Afterwards, as we move towards the mid-span, we can increase the spacing of stirrups. So when you provide stirrups like this, and if you provide the stirrups like this, so here they are of closer spacing because of high shear. As we move towards the center, so spacing can be increased. However, we cannot increase the spacing indefinitely, but there are certain codal recommendations you need to follow when you are providing reinforcement, that is stirrup spacing. I hope this is clear to you. Next, coming to critical section for shear. For critical section, that depends on the support conditions. Say for example, we have a wall here, and on that wall there is a support, and you are going to provide a beam, place a beam. This is a simply supported beam. So from the face of the support, you go for a distance of small d, where small d is the effective depth of this beam. So we must consider shear here, and we have to take that as maximum shear. Even though the maximum shear happens here, this portion, whatever load coming on this, that will be taken care by cantilever action. What it means is, if I assume a crack, shear crack developed in this way, for a distance of d, whatever load coming will be taken care by cantilever action or diagonal compression, and any further load will be taken care by the shear reinforcement. So this is a critical section for shear. That means this is a section where we get maximum shear force, for which you need to provide stirrups or shear reinforcement. So it does not mean that it is not going to be maximum here. Actually maximum is here, but you need to consider this section. That way you can arrive at economical design. If you start from here, yes, you are going to get shear force greater than what you get at a distance of d. See, at a distance d, if you consider the shear here, so shear here will be less than the shear here. Okay? So when you design, you need some shear reinforcement and you provide whatever the spacing required. So what is the spacing we are going to calculate as per the codal recommendation. So if you consider this as shear and provide the shear reinforcement, yes, you can do that. It is going to be safe, more safe. Okay, for practically people, take the shear force here itself. In reality, theoretically speaking, you must take this section. So if I consider this support continued like this, now this becomes the face of the support. This is a support on which this beam is simply sitting. So D should be measured from here. And this is the critical section for shear. And if you cast the beam along with the support, this is column. Again, in this case, D is the distance you take from the face of the support, and this is the critical section for shear. And of course, the load will be coming here. Is it clear to you? Next, if we have a beam, this is a beam of rectangular cross section, okay, and this runs perpendicular to the board, and this beam is sitting on one support on this side and on the other support on the other side, and on this beam there is another small beam sitting. This is a beam. This is also a beam. This is the main beam. This is the secondary beam. Okay? So when we design this secondary beam for shear, in this case, this is the critical section. So we are not going to measure D, where D is the effective depth of the secondary beam. We are not going to measure that distance, and we don't take this as critical section. Instead, we are going to take this section as critical to provide or to design for shear reinforcement. Okay. Similarly, if we have a beam like this, and this beam is not supported from the bottom, instead it is supported from the top. This beam is hung. Okay? This is a beam. Then in this case, we are going to take this section as the critical section to find out the shear force and to design for shear. And this is the critical section. I hope this is clear to you. Any doubt? So now we'll come to the shear part. So, and we will cover what is given in the code book. Thank you.